Hi, welcome to the vodcast on exploration 4.3 about solving quadratic trigonometric equations. If you haven't done so already, go ahead and complete the front side of this worksheet that says warm up. You should be able to do all of this using what you already know about trigonometric equations, also quadratic equations. And kind of we're going to be looking at combining those things together in the new skills for this. So I want you to kind of jog your memory about these important things before we move on. Okay, hopefully you've completed the front side. Now there are a couple things that I want to address on the warm-ups as far as things that I want you to pay particular attention to as we move forward. The first thing in number 1a, notice that what really happened in number 1a is we had very similar expressions except for the first side, the left-hand side, had sine squared in it and the second side had cosine squared in it. And what we did is we employed a Pythagorean identity that changed sine squared into cosine squared, and what we did is we made a substitution for sine squared x and replaced it with, in parentheses, 1 minus cosine squared x. Note that that 4, that leading 4, that's the coefficient of the sine squared term, applies to both the 1 and the cosine squared x, and you need to distribute that. And after that, it all falls out. The other thing that I wanted to talk to you about on this front side is kind of reminding you about strategies for solving quadratic equations. With both of these, the first step is to get one side equal to 0, and then we can either factor or we can use the quadratic formula. If you are not very good at factoring, you can always use the quadratic formula, but I really wouldn't recommend that. I think that it's really important to try to push up against that skill of factoring and practice it as much as you can, especially if you're not inclined to be very good at factoring. So you should always try to factor. Don't sit and stare at something for hours and hours, especially on an assessment or anything like that. There's nothing wrong with going to the quadratic formula, even if the equation was factorable, but factoring remains a useful skill, you know, in situations other than this when you can't use a quadratic formula to kind of avoid the issue. So I do just want to remind you here, what I like to do when I factor is I look at the leading coefficient of the first term and the constant term. I think about what can I multiply together to get 3, and I put these two terms in, and then I think about what I can multiply together to get -8, and I think about how I can put those factors of -8 into my factored form so that I get a cross term of 10. If you really struggle with factoring, you can split the middle term. I just want to quickly remind you of that. That is a strategy that you may remember from, I think, Algebra 1, where you take those coefficients and multiply them together. You get 3 times -8 is -24, right? And then you look for factors of that number, factors of -24 in this case, that sum to the value in our middle term. So in this case, I can say plus 12 times -2 is equal to -24, and then you can go ahead and rewrite the thing that you're trying to factor with the middle term split. That's why then it's called splitting the middle term into these two numbers. So let me show you what I mean. 3x squared, and then instead of writing plus 10x, I'm going to write plus 12x, right, minus 2x, minus 8. Oops. And then what I want to do is I want to factor this by grouping. I want to look at the first two terms and the last two terms, and for each of those I want to factor out the greatest common factor. So what's the greatest common factor for 3x squared and 12x? That's 3x, and what's left is x plus 4, and then I want to think about what's the greatest common factor of -2x minus 8, and I'm going to say minus 2, and then what's left is x plus 4. And now I have an x plus 4 in both of these two terms, right? And I'm going to factor out the x plus 4. So if I factor out the x plus 4, what's left in the first big term? Well, that's 3x. And what's left in the second big term? That's minus 2. You see that we get to the same thing eventually. Now, factoring aside, what is the reason for factoring a quadratic equation is because then I can employ the factor theorem. And this is something that's really important. The idea of factor theorem is that, is that when I have two things that are multiplied together, right? Like in this case, I have 3x minus 2 and x plus 4. When those two things are multiplied together, I have to, if I get 0 as an answer, that means one of the two numbers that I'm multiplying together must be equal to 0, right? I can't have a multiplication problem that has 0 as an answer without one of the inputs being 0. So I say, well, ways that I can make this equal to 0, either this thing can be equal to 0 or this thing can be equal to 0. And then that happens when x is 2/3 and when x is -4. So this is my solution set for this problem. These two numbers will make the entire equation equal to 0. Now the quadratic formula, you should know it. I am going to remind you that you should probably have quadratic program on your calculator. That's what I did to solve this equation, is I used the quadratic program on my calculator. If you don't have one of those, on Schoology, there's a link to a program where you can, or to the lines in a program where you can enter it yourself or type it in, and or you can come to class and get a quadratic formula program put on your calculator in class. So there's an option for that. I didn't do number 3 here yet, but I do want to remind you that what you can do when you have two things multiplied together, even if they're much more complicated than you would get as factors of a quadratic formula, the factor theorem still applies. I have two weird things here multiplied together and equaling 0. And how am I going to solve this? Well, either the first thing is going to be equal to 0 or the second thing is going to be equal to 0, right? So either this is going to be equal to 0, right? And that happens when x is equal to negative 4.5, or the other thing is going to be equal to 0, and that happens when x is equal to 3. If that wasn't obvious to you, I did that just guess and check. The way to solve that equation, because it has the unknown in the exponent, would be with logs. So, yep, they just keep coming back. Anyway, so, all of that is just setting the stage for where we're going with the new material today, which is to solve equations that are both quadratic and trigonometric. So if I take a look at a problem like this first one, I see that it is both quadratic because I have a term that is raised to the second power and a term that is not raised to the second power and a constant term. So that makes it quadratic. And it's trigonometric because I have cosine x floating around in here. Okay. Now we're going to use skills that are common to both our experience on how to solve quadratic equations and how we solve trigonometric equations. We're actually going to start with the quadratic part first. We're going to look at an analogous equation, right? If I look at this, you can see that there's something very similar to this equation, to the equation 3. I'm not going to use x because x is already taken as the variable in my actual problem, so I'll say z. 3z squared, oops, plus 5z, man, I'm having handwriting problems, is equal to 2, right? There's something very similar about this problem, 3z squared plus 5z equals 2, and the original problem. And in fact, really what we did, to get this problem with the z's, is I basically just decided to make a substitution. I said, let z equal cosine x. Right? And really what you did is you replace, every time you see cosine x in that equation, you replace it with z. This can be an intermediate step in solving this problem. You don't actually necessarily have to make a substitution. You can kind of see how you would do it without making the substitution. Some people find it more helpful than others to actually go ahead and write down what z is equal to. But that's a good first step. And now if I can solve this quadratic equation, I then can take that'll tell me what z is, which then I can use to figure out what cosine x is and what x is. So how do I solve this equation? Well, it's quadratic, so I'm going to get one side equal to 0. 3z squared plus 5z minus 2 equals 0. And now I want to go ahead and solve this either by factoring or quadratic formula. I'm going to go ahead and factor. This is an easy factoring problem. 3z squared only has really one choice for how to factor it, 3z times z. And then I want to think about how do I put the factors of negative 2 in here so that I get a cross term of plus 5. I don't have very many choices for how I can multiply two numbers and get negative 2. It's either going to be negative 1 times 2 or negative 2 times 1. Since my cross term is positive, I want to make the multiplication be more positive than negative. So I'm going to put a positive number over here so it multiplies by this 3, which is big. So positive 2, because that's big, and minus 1. If I do that, you can see that it does come out to, plus 6x minus, or plus 6z minus z, which is 5z, which is what I want. This is equal to 0. Setting the first factor equal to 0, 3z minus 1 equals 0. That's true when z is equal to 1/3. And then the second factor, z plus 2 is equal to 0. This happens when z is equal to negative 2. Now I'm not done yet, right? Because ultimately that's not the problem I want to solve. The problem I want to solve is this original quadratic equation that has cosine in it. But now I know that these are the two potential values for z, and z is just cosine x. So I'm going to go ahead and substitute back in. Cosine x is equal to 1/3. Cosine x is equal to negative 2. And I need to solve these using the strategies that we've had in previous sections here, right? Like what angles are there that give me a cosine ratio of 1/3? What angles are there that give me a cosine ratio of -2? And in this case, I'm going to be using arc cosine. Now I can immediately reject this one as having any solutions, right? There's no solutions here. And the reason there's no solutions is because cosine of x is a ratio u over r. Oh, come on, pen. One less try, u over r. And u over r is a ratio. R is always a side of a triangle that is longer than the u side of the triangle. So therefore, this ratio can never be greater than 1 or less than -1. So u over r is never going to be equal to -2. There are no angles that have that property. Now over here, there are angles that have cosine x equal 1/3, and I'm going to find them using arc cosine. Arc cosine of 1/3. Okay, those are all the set of all angles where u over r is equal to 1/3 on the unit circle, r is equal to 1. So I'm looking for where u is equal to 1/3. Here's the u axis. It crosses here at 1 because it's the unit circle. So 1/3 is, I don't know, maybe about here. And there's 2 points on the unit circle, one straight up and one straight down, that have that u value. And I'm looking for those angles. Okay, so if I go ahead and I want to find any one of those angles, they're not unit circle values, so I need to go ahead and look them up on my or use my calculator to evaluate those. So I'm going to do inverse cosine of 1/3. And when I do that, I get 1 in radians. I get 1.23 radians. And that's going to give me, where is that angle? It's right here. This is 1.23 radians. And then all the angles that are coterminal with that, I can go around extra times. Going around an extra time is 1 full rotation, which is plus 2 pi. Man, the pen is just not participating today. Plus 2 pi as many times as I want. And now using symmetry and geometry, I know that if I go backwards, those two angles here, this angle and this angle, are the same measure. So if I go backwards, that's just changing the sign. 1.23, negative 1.23 plus 2 pi n. Those are the set of all angles that have u over r equal 1/3. So my x values that satisfy this equation are x equals plus or minus 1.23 plus 2 pi n. And that's my final answer, right? Because those are the values of x, which make my original equation true. Now, the second problem that we have here has another extra wrinkle to it, because if I look at the original problem, it's still quadratic. I have a squared and a linear term, and it's still trigonometric. I have sine, but I also have cosine. And this is the problem, is that I can't use the strategy that I used in the first problem here when I have some sine and some cosine. So what I'm going to do is I'm going to use something to what I had here on number 1A of the warm-up, right? I'm going to change using Pythagorean identities. I'm going to get this so that the equation isn't all in the form of sine or all in the form of cosine. It's much easier to change sine squared into cosine squared than it is to change cosine into sine. So I'm going to use a Pythagorean identity and replace sine squared with 1 minus cosine squared. Okay, and then the rest of it is still there. Plus 6 cosine x plus 1 equals 7. And now what I'm going to do, I'm going to go ahead and multiply this out for, try that again, 4 minus 4 cosine squared x plus 6 cosine x plus 1 equals 7. This is a quadratic equation now. I want to get everything on one side of the equal sign, set the other side equal to 0, so I can use the factor theorem or the quadratic formula. Even though almost everything is on the left-hand side of this equation, I'm actually going to move everything to the right-hand side of the equation because I find it annoying when the leading coefficient of my equation is a negative number. It's hard for me to kind of think through factoring when that's the case, so I'm just going to avoid the issue and move everything to the right. So on the left-hand side, I want to be left with 0. Moving everything to the right, I get positive 4 cosine squared x minus 6 cosine x. And then my constant term is going to be 7 minus 4 minus 1, which is 7 minus 5, which is plus 2. Okay, so now I have this equation, which I now need to solve. use the same strategies we did in the above problem, make a substitution for z, go ahead and solve that quadratic equation, plug back in, solve the resulting trigonometric equations, and you'll be able to get through that problem. I'm going to have you finish that one on your own, check your answers against the solutions, and then also try to summarize the steps that we take here when we're solving a quadratic trigonometric equation and write yourself a 3-step strategy. I'm going to tell you right now that I want there to be 3 steps, step 1, step 2, step 3, and think about how you can generalize the strategy for solving quadratic trigonometric equations using what we learned here today. That's it.